Okay. We have confirmation that my presentation is there. Yeah, I see it. Okay, so welcome to this session, everybody. Here we're talking about math manipulatives. And I'm going to introduce a microbit method for creating manipulatives that you and your students can build yourselves, embedded with your thinking and your logic and your mathematics, and then use to do mathematics exercises to learn with in class. I'll just remind everybody of the norms that we're sharing for every CSTA session. These are all recorded. I'm not sure whether I'll invite people to open their microphones and speak, so we will be using the chat for sure. I'm going to begin by introducing the organization I come from. I work for Kids Code Jeunesse, KCJ. So Kids Code Jeunesse is a Canadian charity. It's one of those bilingual English-French names that Canadians often use. So we are Kids Code and Code Jeunesse in French, which is the official second language of Canada. We are an 8-year-old organization. We currently have about 70 people on our team, and we're spread coast to coast across Canada. And we're dedicated to giving every teacher and every kid access to digital skills. We have a special campaign going on over the next 10 years. We've committed to reaching 1 million kids directly and indirectly through their educators about AI and ethics, and using technology to address the Sustainable Development Goals from the UN. And what's unique about us among organizations like us, in Canada, there are several like us. We do a really great job of delivering in both official languages, English and French. So related to the underserved issue that Dr. Ko was just talking about, that's a big issue linguistically in Canada. We're very proud to serve both communities there. We were on the leading edge of introducing AI and ethics in our teaching a couple of years ago. And we do have a special focus on reaching girls and children in communities where they are and may be underserved. It's also traditional for us when we do presentations like this to acknowledge where we are based. We're based, KCJ is, on unceded indigenous territory that belongs to the Kanien'kehá:ka. We know them as the Mohawk. That's the English name. They call themselves Kanien'kehá:ka. And KCJ is headquartered in Montreal, and that's where I'm located. The traditional name for that is Jojaga. So I invite you, as we've done in our other sessions at CSTA and elsewhere, if you know whose land you're on, please chime in the chat. And we're happy to support everybody learning about the traditional history of where we are. Final note about KCJ itself. Our model is mostly to be the first few introductory steps for people who are just learning digital skills. So we like to say that our core audience is generalist teachers and generalist kids. We really enjoy creating light bulb moments for people who don't already think of themselves as tech savvy or as contributor to the world. We want to bring a more diverse pool into that world. And our pedagogical approach, largely because we often show up without knowing our audience beforehand, we're a service organization that way, not embedded in any particular classroom, we have to teach coding in a way that supports sense making. And my colleague Matt and I had a session about that yesterday afternoon. That means from the very first moment, we need to help people make sense of what's going on inside technology. They'll have a better chance of being able to appropriate the tools that are inside and do their own things with it. And we find that if we teach that way, we generate very good self-efficacy and, of course, positive affect. So a little bit about what I expect your profile is like, and we'll check the poll results in a moment to confirm. Because you're at CSTA, I assume that you're a fairly experienced teacher. I expect repertoire includes computer science explicitly, or at least a STEM field related to computer science. Because you're in this session, I'm guessing that you do some CS integration, or you support subject area teachers in your school or in your board, You supply the computer science angle, and they supply the subject, and you bring those together. You may have been attracted by microbits in the title, so you may know about microbits and have a supply of them that you can use, or maybe you're curious about them. And you want to try building an exercise or another exercise, if you are, that explores math through code. Maybe you or your close colleagues have some personal connection to math. Maybe you've been a math teacher before. And maybe when you see the word manipulative, you realize that that's pedagogical gold, and you came here to talk with other people about that. If that's the case, you're my kind of people. So let me pop over to the polls. I'm going to close the poll, and we'll take a look at the results. One last chance, 15 seconds. If anybody wants to go from the chat tab over to the next one, which is polls, answer with the oldest grade you tend to teach and the youngest grade you tend to teach, and whether you have experience with microbits or math. Give you 5 more seconds and I'll close that poll. 2, 1. Okay, let's show the results. Deborah, do you know how I show the results? I'm clicking the button that says show results, but I don't actually see them.
Yeah, that's all you're supposed to do is say share results.
Does anybody see the results?
When I click on them, I was able to see them.
You can see the results. Okay. Would somebody like to interpret them for me? Because I can't see them. What do we have in terms of grade ranges?
All right. K through 1 through 2, you had 0 vote, the oldest grade I tend to teach. And then 3 to 14, you had 15.0%. And then 5 to 6, you had 42.9%. And older, those both had 18 votes each. You had 42.9%. So 5 to 6 and older both had 42. Oh, now older.
I see the problem. I didn't answer the poll myself. I need to do that. So,
okay.
I've used microbits, have experience teaching math integrated with computer science. I see. Okay, a lot of people have not used microbits before. Oh, that's good. So we'll do some good introduction. A lot of people here have taught math on its own. Twice as many as have taught math integrated with CS. Okay, we've got a lot to build on here. So this audience is going to be similar to other audiences I've done this workshop with. Typically, I go into a math teacher conference, and I'm introducing them to code for the first time. That's the part that's new to them. So the math side is very, very familiar. I have to get them to understand block coding, which they may have never even seen before. Here, I'm assuming it's the reverse, and the poll bears that out. Okay, we've got people who are familiar with coding and with math. So this is very, very cool. Okay, thanks, everybody. Hey, I see a couple of other Canadians in the chat. It's nice to see you. So here's a rundown of what I'm going to do. I'll begin with a little bit of backing up math and coding and why they work together so well. I'll talk a little bit about math pedagogy, which drives building manipulatives like this. I'll introduce the microbit just a little bit. And then where we're going to spend the bulk of our time is a handful of starter projects. So I'm actually going to code on screen, and I'll invite you to follow 4 starter projects on the microbit that are manipulatives you can build and then use. Okay. Oh, just a final note about me. I'm in computer science education as a second career. I actually studied computer science as an undergrad, ended up in the IT world as a software developer, data analyst, and product manager for a number of years, and began volunteering with KCJ when KCJ was starting out. And you might say I was bitten by the bug. I was teaching my own kids at home and decided to on KCJ and be a part of this wave of computing education and help make it better. And then I'm also pursuing an MA, a Master in Arts in Math Education at McGill University up here in Montreal. So a lot of what I'm going to show you here on the math pedagogy comes from what I've learned from math education research. Okay, we've done the poll. Why is coding such a good vehicle for math? I'm going to touch on this, I think, a little lighter than I expected to, so we can get right to the coding. Not only because on the surface level, there are lots of common terms and mechanisms, things like a variable, an algorithm. Of course, those are terms in both fields, but because coding activates many of the same practices that we're trying to develop in math class. So what you see on the right-hand side are practices from the Ontario math curriculum, and they're very similar to Common Core and NCTM, which is a math teachers organization. This is mathematics, but it sounds a lot like what we want to teach in computer science and computational thinking. And I wanted to share a quote from Mark Guzdial. He's a computer science education researcher. I don't know if he's at CSTA, but he's certainly in the circle of CSTA people. And he comes from the original school of MIT Logo and other children's computing languages. So he's an active researcher now, very influential in that space. And he wrote this at SIGC, the Computer Science Education Special Interest Group of the ACM, just a couple of years ago. When a student writes code, the student is teaching the computer how to complete a task. That's a really powerful idea, and it dates back to Seymour Papert and Cynthia Solomon's insight in the 1970s when they began the field of computing for kids, programming for kids. The idea that you could be the holder of knowledge, and there's this dumb, untaught calculating machine you can imbue with your ideas and your understanding, and then it can carry out things for you. That's a really empowering thing for a kid to feel. And we're going to show here how we as teachers can leverage that to help them get scaffolded in math. I also want to say at the center of both fields, I think if you squint, is that in math and computer science, the core thing we need to do in order to get anywhere is to model an abstract thing that's out in the world so that we can then manipulate that abstraction, that model, and do things with it. Okay, math pedagogy. So one of the greatest math conferences I've been to is the OAME. That's the Ontario Association of Math Educators. They are really closely aligned with the NCTM in the US. This is Graham Fletcher, who's Canadian born, but has made his career in the States. I think he's in Texas, if I'm not mistaken. So he was at the conference the last time I went in 2019. And I'm going to share a couple of slides from him and from Marion Small, who's a Canadian math educator, also one of the leaders here. So Graham Fletcher challenged us to think about, in a math class typically, are we inviting kids to learn math in order to then problems? In other words, here kids, I'm going to teach you some rudiments of math, and then I'm going to give you a worksheet, and you're going to use the stuff I just taught you to solve some problems. Or could we reverse it? And could we confront students with problems, not telling them how to solve them, but to let their thinking emerge and coalesce, and in the process, they learn real math. He also asked, in a typical hour-long math period, who's in control of the learning? Having manipulatives really puts the students in control of their own learning. They are doing things actively and constructing their knowledge much more than if they're sitting and passively listening. So Marion Small showed us a number of rich or complex tasks, problems. Researchers call them tasks. She said, think the way that we ask students to learn about. Okay, students, let's decompose 42 into tens and ones. And she pointed out, if that's the way you pose the problem, you've already decided as the teacher that there are tens here and there are ones here. And those are the multiples I want you to attend to. That's what I want you paying attention to. A better way, she says, to give students an opportunity to think make sense of something and decide how to approach it, is to pose it like ways we could decompose 42 into groups. What you're foregrounding is, here's a number that could be made up into groups. Without even saying more than that, you're implying that there are different ways to do this. And maybe some of them are going to be easier, some are going to be harder, some are going to be more clever, some are a simple brute force way. If you pose the question like this, you let students discover that on their own. Graham-Fletcher has a really of progression videos. If you want to see the overall scope and sequence that elementary students go through from kindergarten to high school in algebra, in numeracy, and things like that, these are very short, hand-drawn and demonstrated sequences. It's a total of 20 minutes or so. I encourage you to go check these out because they're a nice grounding here. And then tips, which is where we're going with the microbits. If you're, like many of you are, you'll be familiar in elementary space with physical, tangible objects that help kids scaffold their way to numeracy. Kids will start with counting little piles of stickers or blocks or cubes, objects of any kind, M&Ms. They'll move up to things that have been designed by educators, like an abacus or Cuisenaire rods, which are color-coded different lengths. And then, over time, you progress them as a teacher to base 10. So now we're talking specifically about the 10 system, and we introduce individual cubes as units, rods of 10, and then flats of 10 by 10. So these manipulatives are just a really great tried and true way to scaffold students towards deeper levels of thinking. And I try to here some of what Graham-Fletcher is talking about in those videos, and you'll see them echoed in any of the standards that you want to follow, the Common Core I've linked here. But basically, starting in kindergarten and progressing up to the late elementary grades, these are all the steps that students should be stepping through in order to finally reach an understanding of the standard algorithms. And we cheat them of the opportunity to make sense and build really robust mental models if we jump right ahead to the standard algorithms, demonstrate them, and ask them to follow. Now, Matt and I did a session at the end of the day yesterday about sense making, and we touched on this theme here too. In computer science, as teachers, the most common way I've seen to lead a lesson is, okay, folks, today we're going to build a rock, paper, scissors game, and I'm going to show you. So follow along with me, okay? First do this, then do this, then do this. Now, there are ways to teach that well, but the easiest way is actually not taught. That's the computer science equivalent of jump standard algorithm. I've done the thinking already. I'm going to download that to you and simply ask you to follow. Some of you are going to introspect and make sense of that and add this to your mental model. Others are just going to stay at a surface level. They may white knuckle it through and get something working, or they may not, and you've lost an opportunity for them to learn. Final note on this, overall you see a sequence moving from concrete, tangible, physical things to representational and to purely abstract. And that really hit home for me yesterday at CSTA day one, where I was in the session with the code.org team. Was anybody else here in that session? Because I think they complement each other really, really well. I'll pause for a sec. Enter in the chat if anybody was at that session. And Deborah, can I ask for a time check? Because I've already sort of lost myself in my narrative, and I want to make sure I don't run out of time.
We are at 2:09, and you have time until 2:30.
All right, we're gonna get moving.
Okay.
Okay, so this is the curriculum development team from code.org, right? They are responsible for creating a full high school level curriculum, computer science principles, CSP, that's gonna get used in schools all across the US. They don't assume any previous knowledge from the students coming in. In fact, it's a strategic choice to gear the curriculum to people who don't have experience, because that increases access and equity. And they've had tremendous success with the manipulatives that they've built for teaching computer science to high school kids. What you see here on the screen is a screenshot I took yesterday of the computer science equivalent of rods and base 10 cubes. This is a paper model of what a variable is. Literally a plastic Ziploc bag with a label on the outside and a slip of paper that gets put inside it, a value. They were very upfront in saying this feels elementary, but it's a very successful way in their experience to get everybody in the class on the same footing, understanding the concepts very well from multiple perspectives, and then decoding much, much faster. Okay, so in the spirit of all this lead up, I'm going to introduce 4 simple projects. They slowly build up in complexity. The code itself never reaches anything beyond what a 3rd or 4th grade student can do in microbits. The intent here is to match the level of math that the kids are at with the amount of code that they're able to do. And in fact, what we're really after is not code that's super complex, that you'll come out able to say, oh my God, look at what amazing thing I got this program to do. Rather, the code itself is done, it takes your thinking, and then it quickly gets out of the way so you can do math with it. That's the whole point of a manipulative. And really the focus of this inside a math lesson, CS and math integrated, is what thinking can I do equipped with this tool that I've programmed. I don't have time for a full microbit routine. Let me just introduce. This is a microbit. I've put a piece of masking tape over the front of mine here, which in our experience in real life, in a classroom with full sunlight, just makes the LEDs easier to see. Microbits are known chiefly for the 2 buttons, which makes them very Nintendo-y and interactive. A field of 5x5 red LEDs, and contacts along the bottom here that allow you to build this into robotics and make a pro. Microbit is very inexpensive. It has tremendous legs. A classroom set of microbits, 10 microbits with students paired up or tripled up, can go really, really far in the hands of teachers in your school in multiple subjects. We became known as the microbit people in Canada a couple of years ago because we traveled with these far and wide. There's lots more that a microbit can do that we're not going to get into today. Really, we're going to follow one simple algorithm here. I'll demonstrate just quickly. One of the things on board a microbit is an accelerometer. So it can tell when it's being tilted or flipped or dropped or shaken. And so one of the canonical projects that people begin with is a rock, paper, scissors game. Rock, paper, scissors, shoot. Scissors. Scissors. Paper. Okay. These 4 projects that I'm going to do, you're welcome to follow along if you'd like to. Open up another browser tab to makecode.microbit.org. I've got a browser already open. It's a very simple algorithm here. We're going to extend it in gentle ways to end up with 4 different projects. The algorithm is this. We need the microbit to remember a numerical value. We're going to do some math operations on it when we click the buttons. And then we're going to show the value, the new updated value, after the operations on those LEDs on that screen. So let me switch my screen share. While I'm flipping, does anybody have questions?
I haven't seen any that you needed to answer. I have answered the ones that pertain to seeing you.
Thank you. Okay.
And now you have 15 minutes.
All right, pressure's on. I'm starting with a new project. I'm going to call this click counter. That is our starting point. You'll see me glancing over at my second monitor here because I'm coding without a net. And as simple as this is, I want to make sure I get it right. live coding is always tempting the fates. So a microbit can be coded with this block programming language, or with JavaScript, or with Python. And just like other color-coded, shape-coded block languages that you've seen, there's a drawer in the middle here with all of the vocabulary that the microbit folks have given us to work with. These are similar to what you've seen in Scratch and Blockly and other platforms, but a little bit different because you're dealing with a physical device, right? So you've got things like show a number on the LED screen, show LEDs that I can individually turn on and off to make an image or a pattern. It's got inputs like, these are like events in Scratch. When a certain button is pressed, or when it's shaken, or when one of those pins along the bottom is pressed, etc. It can play music. And there's a new version of the microbit out since last fall that has a speaker on board and a microphone on board. You can address the LEDs by coordinates, XY coordinates, which is really cool. There is a radio built in, and then you've got additional things here. So by default, it gives you some opening scripts. What do you want the microbit to do when it first starts up? And then is there anything you want it to be doing forever in the background while other things happen? And for these click countings, we don't need forever, so I'm going to drag that away. The very first thing I need to do when I start up is create a variable. I need to keep track of this count that we're keeping, right? So I'm going to make a variable. I'm just going to call it count. And right away, I've got 3 new blocks. This is familiar to you if you watch. And this is also the first place that a math teacher who's never done coding might be a little disoriented, because in the math world, a variable is typically done as a single letter, right? A Latin or Greek letter. Here in the computing world, we use descriptive terms so that we'll know what we're using them for. First thing I need to do when I start up is declare a variable count. I'm going to set it to 0. And then I want to show that number on the LED screen. Here's where I point out this emulator on the left-hand side. This emulator can do virtually anything a microbit can do physically, including being shaken and turned and all those sorts of things. You'll see the little controls pop up when I need them to. So this is another reason that introducing microbits is really cool, because as a teacher, you don't need to physically have a set in order to do these exercises. Right? It's very cool and playable and tangible to have them, but you don't need them. So I'm going to set the count to 0, show that number, but I'm not going to hard code 0, and then 1, and then 2. I need my variable to be in here so that that's going to change, and it's going to show whatever my variable is at the moment. And that's the second leap that math teachers need to take. Understanding a variable inside another command. Okay, so on start, set the count to 0, show that number. And then the only other thing I need to do is when the button is pressed, I'm going to say the A button. I could do A or B or A and B. I need to go back to that variable and change that variable by 1. They've given me that command. And then, once again, I'm going to show that number on the screen again because it's just been changed and I want my user to see that. Okay, that's our first program. It's complete. So let's test this out virtually. And I'll pause. If anybody is coding along, I'll stay here for 2 minutes and you can catch up. So click, 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 click. I'm going to take it all the way up to 10 because what's going to happen when we reach 10? That 5x5 LED screen can only fit 1 character, so the microbit scrolls. And for young kids, this is something they may have seen you know, in a storefront or at a bus stop or at an airport or something like that. So that's a cool little recognition. Okay, I can call this the click counter. It's very simple. And in fact, let me switch my screen share back to the slides because I've got, I'm going to share this very window. Can you see my slides now? This project here, the simple click counter, that's the first one the algorithm is start with 0. When you click the button, add 1, and then show the value. And here are some tasks you can do in class as a math teacher. You can keep score in phys ed class or in any game in your classroom. You can count off steps. You know, another canonical microbit project is a step counter that works by the accelerometer, by shaking, but you can manually count off steps, maybe to measure things. And, excuse me, you can act out simple addition problems. Okay, class, what's 6 plus 3? Click, 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 click. Now, let's go to project 2. And you've got a copy of the slides, and each of these microbit logos is a link to a version of this that I've published. So these are all shared projects you can get to. What do I need to do if I want to make a skip counter? As I showed you in the progression of math through elementary school, skip counting is one of those intermediate steps where a class will sometimes count together. They call it choral counting. Let's skip count by 2s. Let's skip count by 3s. This is a good reinforcing exercise to develop number sense. Well, you would start with 0. When a button is clicked, add some other number. It's not going to be 1 anymore. It's going to be whatever you want to skip count. And then again, show that value. So what's the modification I need to make there? I'll take a suggestion in the chat. What modification do I need to make this a skip counter? I'm not able to see the chat. I should do that. Change the 1. Yeah, okay, change the, yeah, exactly. So instead of change count by 1, let's say I want to make a skip counter that goes by 2. And if you really want to get rich with the mathematics, suppose I have button A doing skip counting by 2 and button B doing skip counting by, let's say, 5. 5 is a real cornerstone number that teachers pay attention to. So here I've built a manipulative that has on button A, I'm skip counting by 2. Button B, I'm skip counting by 5. And if I flip back to my slides, here are some of the tasks that you can do with that. You can ask the Marion Small way, how can you get 24 students with just 2s? How many does it take? And then you're gearing them to do repeated addition and understand the multiples of addition to get to a number. But then you can go richer and say, what are the different ways you could get to 24 or 12 I have here? So then you've got different students in the class who are going to approach this differently. Some are going to go 5, 5, 5, 5, 5, 5, 5 until they bust and go over, you know, like a hand of blackjack. Some are going to go by 2s very cautiously. And gradually they'll start to understand you can play the 2s off the 5s or whatever numbers you're using. Okay. Third that we're going to get to is adding and doubling. Doubling was another one of those key points in the progression. I'm going to get rid of button B. Oh, no, I'm not. Button A, I'm going to make just adding by 1. And button B, I have to go meta here. How am I going to get button B to be a doubler? I can think of 3 different ways as a programmer that I can double the variable count. I'm going to blow up a minute here and ask, what are the different ways you can think of to double our count? Mike Harvey says change count by count. That's definitely one way. Can you think of another way for us to double the variable count? Bit shift, yeah, there's one in every crowd, John. Yeah. I can change count by count. I can, it's a little more roundabout, but I can set count equal to 2 times count. Or I could even set up a loop that repeats count number of times that increments by 1 each time. So You can make it sophisticated if you want to.
Mike, we have 5 more minutes, so
Excellent.
we
Okay.
can get on with questions.
I had a transcript here where I tried this with my own 4th grader at home. I said, how can you get to 12 different ways? And he gave me 3 answers. He said, well, first I count up to 6 and then double it. Okay, give me another way. I'm trying to be pedagogical here. Okay, I'll quadruple it. Well, I said, I wasn't going to just accept that. I said, quadruple, what do you mean? Oh, okay, well, get to 3 and then double it 2 times. And then we tried another and he went bust. He got up to 8 and then tried to double it again and he had to backtrack. And this is a nice little routine. I tried it at home and it was cool. Okay, I've got 2 more projects that I've posted, but I'm not going to step through in the interest of time. One is to make your microbit a single digit. When you get to the point where you're talking base 10s and so if I were in my code here and I were just counting up, I would insert a conditional. I would do a logic check. If I've reached 10 after my latest increment, just set count back to 0. And if I do that, then I've got a single digit that loops 0 to 9 and back again, right? And I've even tried this with teacher. I have 3 of them, each build their own digit. I have them stand, 1 in the place, 1 in the 10s, and 1 in the 1s. And I give them an arithmetic problem, a 3-digit addition or subtraction problem, and ask them to act it out with carrying, things like that. Okay, so you've got the basic template. You've got access to the projects here. Just to recap, these are click counting projects. This is you and your students building your own manipulative where the code is very, very simple, but you need to understand math and a little bit of coding in order to get it to work. And then once you've got it working, use it to do math in the way that Graham Fletcher proposed. Solving problems to learn math. Okay, I've linked further up to the NCTM and the Common Core. If you've got a math teacher that you're supporting, or if you yourself are the math teacher, and you need to make those links, you can show your administrator, or you can show your team, hey, this microbit is helping us reach these goals, and it's a very, very accessible way to do that. So, okay, you can go further with microbits in the middle grades and high school because there are sensors on board. You can think of this not as a manipulative, but as building your own instruments for science class, for example. And I'll stop there and see if there are any questions. Juliet has pinned my slides. Thanks, Juliet.
Yeah.
I've thrown a lot. I took a lot of time to talk about the pedagogy, and I hope that was useful.
It was useful. It was very good information because then the other ones being the practical part people can follow. So that was wonderful. Make sure you don't leave before filling the survey, which is found right there at the top on the same place with chat, poll, people, question, survey. Be sure to let Mike know what a good work he did. We all enjoyed that. And you can continue to hang here asking questions. Mike will be here answering as many questions as you all want answered.
Thank you, everybody.